All right, our next section is 3.8, approximate linear relationships. Scatter plot is a graph in the coordinate plane of the set of all XY ordered pairs of bivariate data. By the way, we've been dealing with bivariate data already, so, as scary as it may sound right now, we've been doing it already as it is. So scatter plot will help us to see if there is a relationship or correlation between two things or variables. Because sometimes there's no correlation, and again, depending on how you use the statistics or how you draw your graph, sometimes you can say there actually is a relationship when in fact there is none. Okay, so be very careful. Draw a scatter plot for the data in the following table. The following data is for the first and second quiz scores for 7 students in a class. Plot the points in the grid below, then sketch a line that best fits the data. Oh, okay. Now, and I think some of you guys have done this on the last, maybe it was this reality check. I don't recommend doing it, again, just because it can come across as being slightly manipulative. Well, first of all, you got to label your axes no matter what. And so X, will say this is the first quiz, which is the X values. It shows there, first quiz score. And then the Y-axis will be the second quiz. I think it was the second quiz. I think these are quizzes. So at least we have it labeled now. But then when we put the scale on, and this is where, just be careful using this in the future, unless you're really trying to mess with people's brains. I would always recommend starting with 0, even if your values are kind of far beyond it, just so we can see exactly where it is in relationship to 0, because 0 communicates quite a bit, actually. So we need 34 and 42 on this. We'll just say each line represents 1, so there's 10 right there, and 20, 30. Oh, maybe I won't make it. Looks like we're going to say every line represents 2, so there's 10. 20, 30, 40, and 50. And I think that's as far as we need to go on, well, maybe we went too far on the X values. That doesn't matter, no worries. And we'll keep the scale the same on the Y value, so that'd be 10, 20, 30, 40, 50. And I see all the Y values go up as high as 50, that's okay. Let's start putting in these points. Now, just keep in mind on the homework, when you put these on, you want to be as close as you can, as close as possible, but if you're off by a little bit, usually there is a little margin of error there for you guys, so if you make a little mistake, it should be okay. And let's put these points at 34 and 42. 34 right here, and then 42 would be up right there. I think I got that one. And then I got 32, 40. So 32 and 40, I think right there. Yeah, it seems right. And then 20, 35, there's 20. And then 35 would be right in the middle there. And then 47, 50. So 48 and then 50. Yeah, about right there, something like that. And then 32, 43. I know this is compelling stuff, you guys. I think it's right there. And then 38, 45. 38 and 45. Boom. There we go. Well, what is that? 6 points. I got all 6 on there, and that looks pretty good. We got it labeled, and we got it scaled. We're in good shape. So this would be the graph that we want, except for I think they wanted us to graph the line that best fits the data. So it's a line of best fit, you guys, which means that you do get to eyeball this thing. All right. Now, what you should not do is here's what you should not do: is say, hey, there we go. This line represents the data. Okay. Well, maybe you'll have a good career in politics someday. All right. Maybe you'll say, maybe you think, well, it looks something like this. Okay, that's really jacked up, you guys. Don't do that either. It should be pretty representative of these values. And yeah, 6 really isn't a lot to go off of, but when you guys graph these lines on the computer, you just got to choose 2 points. Now, this is going through some of the points, by the way, which just, I mean, it just kind of happens to be the way that I've drawn it. But it doesn't always go through, actually, any of the points sometimes. But it also doesn't always go through the endpoints like you guys see that I have right there. And maybe it wouldn't have if I had drawn that a little bit better. So there is some leeway on this. If you didn't have this drawn exactly the same way that I do, because we're just eyeballing it. And yeah, in a real stats class, you'd say, well, we can figure out the equation for that. That's true. But for 980 class, we're just like, hey, let's just eyeball this thing and be good. But you don't want to, again, you got to be pretty close on this, okay? So there's our line of best fit. It just said to sketch it. That was it. Most real-world data does not fall perfectly on a line, just like we just saw. However, the data on the scatter plot resembles a line. We can fit it into a line to represent the data. Then we would also write a function for the line and use this function to solve problems and make predictions. The line that you use to represent the data is called the line of best fit. The most common way to find the line of best fit is to use the eyeballing technique, which is what we just did, and simply try to draw a straight line that best fits the data. The y-intercept represents the beginning value or some kind of initial value on these. You'll have to remember that for the homework, by the way. Now this, I think sometimes they refer to this as like linear regression. And why is it called regression? Maybe I just don't understand what regression means, and I should look it up, but I don't. So it's called linear regression from time to time, and you would say the equation that results from this is the function. Right? You could write a function which is just the equation for this, and then you'd use the function to predict maybe future values or maybe values that used to exist. But part of the problem with that is that we assume that the pattern is continuous in that way. So even straight lines sometimes can curve eventually. So we have to be careful with how we use that data. But there's a lot of data out there that they use for, I would say it's manipulative purposes because it is manipulated, and they say, look at this line and look how bad or good things are, when in fact the line shifts later on. So if the temperature will be 21 degrees, what would be your expected sales? Within $30, which is pretty good. It's a pretty good margin of error because it's really $60 of error that we can be off on this, okay? Because it can go up 30 from where it should be and then down 30 from where it should be. Well, this is 21 degrees. And so it didn't say Celsius, but we get to assume that it's Celsius. Well, 21 degrees, and we don't really need the equation for this one because we can see 21 degrees right there on the line, right? So this is 21 degrees in Celsius. So I would just follow this up until I reach the orange line right there, which is the predictive line, the line of best fit, the linear regression right there, and it gives me this point right here, right? Well, approximately how much would that be in sales? So I'm going to follow this one back to the dollars over here. And, you know, again, you're estimating. You may not come up with the same number that I do on this. You know what? I'm going to say that's 475. All right, so if you said 480, that's fine. If you said 460, that should work. But for us, again, we have a margin of error of plus or minus $30. So even though I may not be right on the money, and I don't think that I am, but I don't have to be on the money on this one, okay? It's just, this is a predicted approximation of what we would expect the sales to be if it was 21 degrees outside, I guess. So this is the same thing, by the way. This linear model, f of x equals 0.45x equals 18.95. It's the same thing as we just barely did. It's just that it's a little bit more exact and it's in numerical form instead of its graph form. Which, whether you say that's more convenient or not doesn't really matter. It's f of x equals 0.45x plus 18.97. I'm rewriting it so we can work with it. But right here it says, well, what if x is 8? Well, go ahead and replace your x's with 8 then, okay? So it's f of 8 now, and I replace the x value with 8. So we still end up with f of 8, whatever it is. And from here, I'm just going to go to the calculator, you guys. And I don't really need to worry about putting this or doing it in my head, right? So I get 0.45 times 8, and I just put times 8. I didn't put in parentheses, but you could. Plus 18.97. I push enter, and it gives me the answer as 22.57. It did say it around to the nearest thousandth. It doesn't look like we needed that. Since it doesn't really tell us what this statistician was calculating, I guess we can't label it either. So we'll say this is our final answer right there. This one's it's a little bit more wordy than it maybe should be. In fact, there's a couple of extra calculations we'll have to put into this. So data on tuition and mid-career salary are collected from a number of universities and colleges. I don't know if this is an actual value or linear regression model they came up with, but in any case, the result of the data collection is this function, where x is the annual tuition and f of x is the average mid-career salary of graduates, both in thousands of dollars. So this would be 164,000, and this would be $890. Negative, I guess, right? Multiplied by whatever x is, because they're both in thousands. So according to this model, what is the average salary of a graduate of a college or university where the annual tuition is $72,000? And then what's the slope of this linear regression model? Well, I mean, you could say it's negative 0.89 right now if you'd like. Or just, if you wanted to describe it, looks like you lose $890 for every year, I guess, of because X is annual tuition. Yeah, I'll have to think more about that. But let's get started with this other part. But that is the slope, by the way. It's just the coefficient of X, just like we've been seeing a lot here in the past. Okay. So we got f of X equals negative 0.89 X plus 164. Well, on this one, the tuition is 72 grand, and since we're looking at this in thousands, it's 72 of those thousands. So that's the value we're actually going to replace the x with on this. And the annual tuition, by the way, is the x value, so we know to replace the x with that 72. Now, if it said that it gave you an average mid-career salary, then we would have replaced f of x and had to solve for x, which would have then told us the annual tuition of the college or university here. Now, again, the nice thing about this is, yeah, we can replace that x as well with 72. But I can type this into the, let me see if I can get this pointer to work. Yeah, the reason why we're using 72 is because everything in the equation is based on thousands. So where this is $72,000 of annual tuition in thousands, it's kind of like we said, you're just going to move that decimal 3 times to the left to make it 72, which converts it into thousands. One of the reasons I like to see this 72, and one of the reasons I like to see 72 as the x is because when I solve this, which I'm going to do on my calculator here in a second, it's going to tell me pretty much an ordered pair. And you'll see it as, 72 and whatever the y value ends up being, which then would allow us to graph it. So the 72 as a function is important because it does communicate what the actual x value is and then what its corresponding y value is. Now, did we have to write it like that? No. The only reason that I did it like that is because they used the function notation up here at the top. Now, be careful on this because the answer that we get, this 99.92 from the calculator, the answer is not 99.92 because that would be, that'd be really low mid-career salary. But we have to remember that this was in thousands of dollars, right? So we need to multiply. You could say multiply by 1,000. Some of you guys would say I'm going to move the decimal 3 times to the right, which would then give me 99,000. Wait, let me make sure. Now, I was going off the track there. That would be the mid-career salary on that one, $99,920. And again, this would be part of the ordered pair. You'd keep the decimal for the ordered pair because the 72 was also in thousands right there. So that's how you use that linear regression model, that function, to, again, that would be predictive. Now again, does that mean that all mid-career salaries where the tuition was 72 grand, are they all going to be 99,920? No. It's just a good way, well, it's a way to say that look what we found. If you had this annual tuition, then you can expect to make mid-career this amount of money. And I mean, I hope you guys can see how manipulative that can be, because averages assumes that everyone is the same, which in fact is never actually true. So be careful on those. Alright, Alejandro is selling HDMI cables on eBay and is trying to determine the best price to sell at. For the last 10 weeks, he has adjusted his price slightly each week and tracked the number of cables he sold. He plotted the results and drew a line he feels fits the data well. The line of best fit passes through these 2 points, so we need to make an equation, and it's going to be based on those 2 points. We can't really eyeball it for the equation on this one. Which really means that, I don't know, the graph really doesn't really help us on this one. So, because I need the space, goodbye graph. Oh, that didn't work. Let me try that again. Goodbye. All right, we did it. We got the space we need. Well, what does this mean? Well, it goes back to the last section, right, where we were writing equations that pass through 2 points. There it is, 2 points that this goes through. So we're going to find the slope first, and yeah, we are going to write this in slope-intercept form. And we're going to use the slope formula first. And the first point that I see is 4.75. I don't know. Maybe I could have used the 3.5, 280 first. It doesn't matter though, because it's just slope. 240. And also we got 3.50. You don't really need the 0 on that, so I'm just going to show us 3.5 and 280. Right there, okay? So these calculations aren't too bad, you know, just directly this is negative 40 in the numerator. And 4.75 minus 3.5 is 1.25. Well, I can't do that in my head though. So I'm going to solve it on my calculator. So we got negative 40 all over 1.25. There you go. Negative 32. All right, now we could interpret this, by the way. Well, maybe that's where I do need the graph. Dang it. Well, it's comparing, what is he comparing? Weeks and money, right? So it looks like whenever he lowers, all right, so yeah, it's quantity and price. So it looks like he loses 40 sales in quantity in sales, for every time he raises the price by $1.25. Oh yeah, you'd expect to probably lose sales if you increase the price. Not that that always happens, but it is the case for Alejandro. So we got the slope in any case, and now we're going to finish writing this equation in slope-intercept form, but converting it from point-slope form. All right, so we got x minus the x value, and then we'll put the y value in there. And we do know the slope is negative 32. That's good. And we can use either one of the points. I'm just going to use that first one as 350. So that's my x value right there, 3.5. And the y value is 280. So that's a positive 280. Right here. Right there. So now we're ready to distribute the negative 32. And I'm going to employ my trusty calculator for the decimal multiplication right there, but I get negative 32x at least. So here comes that calculator again. Negative 32 times it's a negative 3.5, you guys. Oh, I missed the decimal 0.5. And I push enter, and it gives me a positive 120, 112. There we go. But we still got this plus 280. So this is what y is, and we'll simplify this further. We got the slope is negative 32 times the x, but we can combine these two. Looks like it would be a positive 392 on that one. Now, this isn't actually the equation that they wanted. They wanted it in terms of y, which is the q of p right there. So we're going to replace the y with q of p. It's the quantity based on the price. And this equals still the same slope, negative 32, but again, they don't want us to use x on this one. They want us to use p on that, so there's our p. It's the same p in the function notation right there. And plus our y-intercept, yeah, we found that, plus 392. Bam. Yeah, so I boxed it in to make it official. Alright, so there's our function, and it says, using this model, predict the number of cables Alejandro would sell at a price of $3.65 to the nearest whole cable. Alright, no problem, man. So this stinging chart, I'm going to have to get rid of that because I need the space. Again, there we go. Alright, so we got Q of P, but we know the price now, in this case, is $3.65 equals negative 32 times that $3.65 plus 392. Alright, so how many will you sell, Alejandro? Let's find out. 3.65 and then 3.65. So that's going to be Q of 3.65 equals, let's put that in the calculator. Alright, so that's what we get. 275.2. Now this is not labeled in dollars, right? The 365 is dollars. So this is actually cables, but it did say to round to the nearest whole cable, so we'll just make it an even 275 cables. If his price was $365. A hospital has been tracking the number of incidents of heart disease it treats each year for several years. The data is shown below. The data is approximately linear. Well, that's okay, because you could draw a line of best fit if you wanted to, but we don't need one in this case because it says, use the data from 2012 and 2015 to find an equation for the linear model. Okay, here's what that means, you guys. Is it's saying we only want to use the years 2012 and 2015, so ignore that garbage between, because we don't care how it was changing in between. We're just going to use these two values. And again, that's where, depending on how your numbers look, it could be quite manipulative. But it says use the variable t for years after 2010. So in other words, 2015 would be t equals 5, where n of t is the number of heart disease incidents. N of t just represents our y value. Well, here's what we want out of this, is the linear model of this, which is the equation, and we'll write it in function notation after we get this solved. But before we do, we're going to have to figure out what the slope is, right? Because we always need the slope, and then we can use one of these, and these are ordered pairs, by the way. We'll use one of the ordered pairs to figure out what am I thinking? The y-intercept? Yeah, I think that's good. Yeah, because we'll figure out the slope and then the y-intercept. I may have lost my train of thought on that, so if I didn't make sense, hopefully by finishing it will. So the slope, right? Try to keep this consistent. Green is m for slope, and we got slope formula on this one. Now in 2015, Yeah, we'll say, 2012, doesn't matter. 2012, and yes, the years have to go in the denominator because it's the independent variable, and the dependent variable, the heart disease incidence, will depend on the year. So that's our dependent on that one. It was 74 in 2012. And then we'll look at 2015, which had 92 incidents. So this ends up being, what is that, negative 18 over negative 3, which really simplifies into 6. If you had reversed those, you would have gotten a positive 18 over positive 3. That's the only difference on that. But you still end up with 6, which is nice. So the average, and this is the average, by the way, is 6 heart disease incidents per year on this one. I kind of ran out of space right there. Well, that's the slope, by the way, and I probably should have drawn it in green, but whatever. Well, from here we can use point slope form to figure out the final linear model for this one. So I'm going to go back and say the slope is green is 6 heart disease incidents per year. And then we get to choose which of the 2 points we want. I just use the first one. Now the year 2012, that's where the T or the X in this case, we're just going to use 2 on that, okay? Because it says 2010 was year 0, the first year, right? Or we're looking at T years after 2010. So 2012 was 2 years after that, so we have a 2 right there. As a general rule of thumb, when you look at a table like this, the X values are always on the left and the Y values are always on the right. If they didn't do it that way, then they jacked it up real bad. Okay. Now, on the other hand, though, it all has to do with dependent and independent variables, which is, it may be more scientific or more understandable in science, even though they stole it from math, the jerks. But we know that the heart disease incidents are changing based on whatever year it is. So since it's changing based on a year, it depends on what year it is. And whatever you get that depends on another, that's the Y values. So the independent variable, which in this case is years, is the X values. And again, this is just a general rule of thumb. It's only false from time to time, but when you look at time, whether it's years, seconds, minutes, hours, doesn't matter, those are usually independent, usually. Yeah, so the 2 comes from it being the year 2012, right? Because I'm using this ordered pair right here. But it says that we're looking at years after 2010 right there. And 2012 was 2 years after 2010. So that's where this 2 comes from. And yeah, if you put 2012 on that, you're going to get, well, quite a big negative number, which wouldn't make sense in terms of heart disease incidence. At least at this rate anyways. I'm not a big fan of them saying that we're using a different initial value. Usually we go off of zeros, right? But the nice thing about this is it does show you that, you know, if you want to make an initial value a certain time, again, that goes towards what could be very manipulative about data. You can observe numbers based on a different initial value if you need to. Yeah, and yeah, there's a lot of letters and numbers going on, you know, MX, B's, Y's, and now, you know, we're going to change it into function notation. But if we can focus on this being in its regular point slope form or slope intercept form, changing it back into function notation really, hopefully, isn't too bad. So now that we got that, yeah, we need to distribute the 6 into the parentheses right there, right? That gives us 6x, and then 6 times negative 2 is negative 12. Still got that plus 74 there. So this is what y equals, and just simplify it from there. We got the slope is 6. Multiply that by x, and we'll combine negative 12 and positive 74 to get 62 positive on that one. Now, again, this is general slope-intercept form, but it wanted us to write this as a linear model, a function. So the n of t, let's see, that's this stuff right there. That's the y value. So it's now n of t, which equals, and the slope is still the same. It's 6 heart disease incidents per year. But then again, instead of x, they want us to use the t. So it's t's on this one. And then the positive 62. There it is. And yeah, I know we're not done with that quite yet, but that's the function right there. To solve this next problem, using this model, predict the year in which the number of heart disease incidents will reach 146. Now remember, heart disease incidents is 146. That's represented by n of t. So we're going to replace n of t, both of them. It's the whole function part, because that represents the heart disease incidents with 146. All right, so this still equals, it's 6t, we'll use t for time, right? Time in years. Yeah, equals 6t plus 62. Oh, well, this becomes an equation, a two-step equation that we can solve pretty quick, right? Yeah, just subtract 62 right here. Let's see what that gives us. That zeroes out, and that's good. We got 484 right there. Equals 6t, and then divide both sides by 6. So t equals, let's see, what is that, 14 right there? Now, it's not, the answer to this would not be 2014. I mean, we can see the year 2014 in the table right here, right? So it definitely is not 2014. We need to remember what t equals 14 means. Well, t is the number of years after 2010. So that means you're going to have to take this and you're going to have to add 2010 to it, and that will tell you the year that you would expect 146 heart disease incidents to occur, which would be the year 2024. I'll just put year. I feel like I have to label it because it's a word problem, you know what I'm saying? So there we go, the year 2024. Yeah, there it is. An online retail company tracked the total number of monthly purchases. In April 2007, there were 3,820 purchases, and in March 2008, there were 4,260. The purchases followed a linear model of the form S of t equals R t plus I. So R would be the rate, and I is what we would call the initial value, I, where S of t is purchases in thousands, and t is months, where January 2007 equals 0. So our sales increasing or decreasing, and by how much? Okay, well, this first part, hopefully it's not too bad, right? We can see that in the earlier month, or the previous year, I guess, they had 3,820, and then suddenly they're pumping out 4,260. So it definitely is increasing, right? So it's increasing. Now, when it asks by how much, you couldn't say, well, I'm just going to subtract those two and then tell you how much. What it's really asking for is a rate. Okay, it's asking how much is it changing on a monthly basis. So this becomes a slope formula type problem. And yeah, we can say, let's see, April 2007, that would be whatever, the 0th month. I don't know. If you want to say it was the 4th month, right? That's April, January, February, March, April. Yeah, 4th month, it was 3,820 purchases. And then in March 2008, so that's almost a year later, April, January is 13. That's January 2008. January, February, March, that's 15 months after January 2007. But it's 4,260 purchases on that, okay? Well, we can solve this, and that would tell us the slope. So let's pull up the calculator again. 3,280 minus 4,260. So yeah, it was now mine shows negative, but the denominator is going to be negative as well. So that's not a problem. Yeah, that's going to be a lot easier to work with once you type it in correctly, like hopefully you guys did. Negative 440, because now when we divide, we simply get 44. Now, this is answering how much, by the way. Well, that's purchases. So we'll write that in. Purchases, if I can fit it. Purchases per month. All right, so it's increasing. Oh, I'll move the calculator. By 44 purchases per month. And that answers that question. Now, of course, this is going to lead to that function that we have up there, S of t equals RT plus I. And we know the R already. That's the 44 purchase per month. Okay, we just got to figure out an initial value maybe to write this in. And the initial value will be however many purchases were made in January 2007, which we'll figure out. So 44 purchases per month. Write out the linear model function with the parameter values. Okay. Well, this is going to take us back to point slope form. So we got y equals m, which is the 44 purchases per month. We got x minus the x value plus the y value. So I'll put in the 44 there. And we already showed that April 2007, well, I said it was the fourth month. But the problem with this is January 2007 is the 0th month, which means February is the first month, March is the second month, and April is the third month. So it's actually the ordered pair 3,820. Now, if you think that's confusing, you probably should, because it's kind of jacked up that they used January 2007 as 0, but that's the way they did it, okay? So the actual ordered pair that we end up with is 3 as the x value, and then positive 3,820. I'll make sure I wrote that in right. Yep, as the y value. And from here, we can solve this. Well, we'll distribute the 44. We get a 44x there. And then 44 times negative 3 would be negative 1,000. My brain's off right now. I'm going to do it in the calculator. 44 times negative 3. Negative 132. Of course, we still got that plus 3,820. So we'll combine those two together, which will tell us y equals 44x. That's okay, we still know that. But yeah, we need to combine these two. So I'm going to go back to the calculator, add a 3,820 to get 3,000, positive, 3,688. Well, that's a pretty good function right there, actually. And we feel pretty good about that function. The problem with this is it says that it wants the purchases in thousands. So I'll get rid of that calculator. It wants the purchases in thousands. Oh, that stinks. So what this means is that we need to write this function, S of t, in thousands. So all this really means as well is that we're going to take each of these values, the rate, and the initial value, and move the decimal over 3 times. So this ends up being 0.044x. And x. And also the initial value there, because again, this is in thousands. We're going to move it 3 decimals to the left rather, which makes it still positive 3.688. And, oh, sorry, I used x on that. I should have used a t instead. Well, that is actually the function that it wants, okay? And again, it may come out as quite confusing because we needed to change all those values into thousands, and we just did. But that is the function. That feels like. Now this part says, what does the model predict total purchases will be in June 2010? Well, we got to figure out when June 2010 is in relationship to January 2007, right? Well, here's something that we should know from this, is that every January is going to be another 12 months away, right? So that means that January 08 would be month 12. So January of 09 would be 24 months. Hence, I don't know, something like that. So January 2010 would be 36 months, right? Well, from there you can count to June. And right here we see February would be the month 37, March, again, this is 2010, month 38, April, month 39, May, month 40, and June of 2010. The month we're looking for is month 41. Well, it's the month that we have from this, so we're going to go in and we're going to replace T with 41 in this function right there. So yeah, instead of T, I should put 41 right there. So this equals 0.04, I think we had 44, right? Plus, yeah, so it looks like this one, they approximated those values, but I don't want to approximate right now. There's no need to. So I'm going to put this into the calculator, which will tell me, what is this, the purchases, right, that we would expect in June 2010. So let's go to the calculator. Now from this I get 5.492. But again, this is still in thousands, so we just need to replace this with thousand. Just multiply it by 1,000 if you'd like. You'd get 5,492 purchases. And again, this is for June 2010. So there's our formula, and we got to figure out what month and year does the model predict sales will be 5,780. And again, it's still based off of January 2007. Now this is asking purchases, right, which is S of T, so we're going to replace that with the 5,780, and this becomes an equation that we can then solve. So we would subtract 3.688. Oh yeah, and seeing this shows that we need to change the 5,780 into a decimal, which would be just divided by 1,000 or move the decimal 3 times to the left. You get 5.780, and you don't need that zero there. So now subtract 3.688, and let's see what that comes out as. Yeah, so we subtracted that, we get 2.092 equals 0.044 T. And then, of course, the last thing we'd want to do is divide both sides by 0.044 to make that a phantom 1 there. But yeah, if you do it one side, you got to do both sides. So T, this is the month, right? 2.092 divided by 0.044 in my calculator. And, well, maybe we'll round it. It's 47.54. So we'll just round this up into 48 months, okay? So we'll say T equals 48. So this is 48 months after January 2007. Well, 48 is a nice round number because every year is 12 years, and 48 is a multiple of 12. So to figure this one out, we'll just add 4 years to January 2007, which puts us at, in actuality, January of 2011. So that is when we would expect there to be 5,780 purchases based on this linear model. And you would hope that a business that's been around that long would maybe have a little bit of exponential growth, at least a little bit, you know what I'm saying? But for what we have, that's the answer that we get.